What now? Can you hear me down there? Is the microphone working?
It was, now it's not.
We can hear you.
We can hear you.
All right. Good enough. Let's get started. I've got an hour to for 50 minutes to kind of share with you some of the details of nuclear engineering. Dr. Imel touched on some of it last time. I intend to go into a little more detail than he did. Kind of just, well, I entitled this presentation, Why the Fuss? Why is this important? What power is there? How much is there? Maybe give you a feel for how it scales with some of the alternatives and why it's important for our future. Let's start with a kind of a real brief review of matter. If we take the standard model of the atom consisting of neutrons and protons surrounded by electrons. All of the ways we get most of the ways we get our energy today are all chemical in nature. And that's all involves rearrangement of the electrons in the outer shell mostly. And so the energies that are involved there are fairly meager compared to the energies holding together the nucleons in the nucleus. So by rearranging the nucleons in the nucleus, there's lots more energy available for us to use, for us to get at, than the rather weak interactions that occur through chemistry, which is rearranging of the outside electrons. So the basic review, if I start with one proton, we call that a hydrogen. Of course, the protons have a positive charge, and you have to have an electron on the outside of that to balance it. If we have two protons, then we create helium, and we move on up the chart by adding one proton after another. These protons, the more we add, the more neutrons are required in the nucleus to keep the atom stable. So we found two ways to really represent this. The first, you're probably familiar with from chemistry, is that if we start, we can draw this periodic table. So we draw this periodic table by putting hydrogen over here, putting helium over here on the other side, so forth. And then as we add one more, we come down here to lithium, beryllium, and then we skip over to the other side and have another 6. And we build up this table like this. Now another row here of 8 blocks, and then we fill a full row across. What we're really doing here for this periodic table, which you've seen in chemistry, is we're arranging these things according to how many valence electrons, or how many electrons are in the outer shell. So here on this edge of the table, we have essentially one free electron out in that outer shell. On the other side of the table, we have a full outer shell. In the case of the inner shell for helium, that consists of only 2. The next shell up takes 8 more. So the next one up here will have 10. So forth. Okay? So you're probably familiar with that way of looking at things. Another way of looking at the structure of the nucleus that's kind of important. Actually, here's a full periodic table that you can see on it. Another way to look at things is to draw what we call a chart of the nuclides. So what I'm going to do down here is I'm going to make a little chart, and I'm going to plot on one axis of this chart, the y-axis, what I'll call Z. Z is just the number of protons. Down here on the x-axis, I'm going to plot N, the number of neutrons. And I can draw any particular element as a series of boxes along that z-axis. Now, a particular element can have different numbers of neutrons. We call that an isotope. What makes it an element and what governs the chemistry is the number of protons, which is responsible for the number of electrons. So different isotopes, different materials of the same element that have different number of neutrons, all behave the same chemically, which makes them tough to separate, as we'll see in a second. So if I were to do something like this, we can start down with a 0 count for neutrons, 1 count for protons, and we have one box right here. We could also have a 1 and 0, right, which is just a plain neutron. As I add these up, I end up with more and more neutrons being required to make stability. So if I had the exact same number of neutrons as protons in this drawing, I would end up with a 45-degree line. Agreed? But we don't see that in nature. We see something that kind of falls off like this, where the stable atoms, as higher we go, the more and more neutrons are required to stabilize this. There are quite a few elements that have a whole series of stable isotopes around this island of stability. Now, if I get too far off either side of this island of stability, then things become radioactive. Okay, they become unstable. And they'll want to spontaneously change in such a way as to return back close to this stable ratio of neutrons and protons, depending on their mass. So one can imagine two different things that will happen. Out on this side of the curve, elements end up being neutron heavy. And so what do you want to do if you're neutron heavy to get back to this island of stability? What they end up doing is shedding some neutrons, and they do that by a process we call beta decay, meaning that actually a neutron comes apart, emits an electron, and becomes a proton. So they move up diagonally on the chart. In fact, down here for a free neutron is radioactive with a fairly short half-life. It will turn into a hydrogen atom. Anyway, things down here will end up beta decay. Things up here go the opposite, where a proton wants to capture an electron and become a neutron. And they will then move down towards this island of stability. Radioactive isotopes, as we'll see next time, radioactive nuclides, are very natural. They occur all over the place. In fact, where does this stuff come from? There's only two particular sources for radioisotopes that we find. Either they have to be primordial, meaning they have long enough half-lives that they're still around from the last supernova event, in this case the uranium, thorium, some of the very heavy things, or there has to be some mechanism that continually refreshes and makes them. In the case of a lot of the nuclides of interest, they're either decay daughters of some of the long-lived isotopes, or they occur by some interactions in nature. Carbon-14 is a classic example. We use that for dating. You've all heard of radiocarbon dating, where you're dating the age of something that's died, something biological that's died. And the process behind that is this carbon has about a 5,700-year half-life. It's made by interactions of cosmic rays with nitrogen in the atmosphere. So the cosmic rays come in and it hits the nitrogen, creates it to a carbon-14. There's a certain ratio of carbon-14 to carbon-12 that's dependent on how strong the cosmic ray flux is coming into the planet. And as anything that's alive is constantly overturning these cells, so we end up with a stable ratio of carbon-14 to carbon-12. Very well established. I could take a sample of your flesh, I could weigh it, I could measure its output of this carbon-14, and I'd get the same number for all of you, because that ratio is very well established. But once you stop respirating, once you pass away, then you're no longer creating, or you're no longer breathing in this carbon-14. So the carbon-14 starts to decay, and over time, you get less and less and less as it decays away. That's how we do carbon dating. You see it misused in the media all the time. People talk about carbon dating rocks and carbon dating other things. There are other techniques for those, but carbon dating is basically using a radionuclide that is continually refreshed or continually created naturally within the environment. Okay, let's see. If I can get back to the computer here, I pulled up a couple of things. One is this chart of the nuclides. There's a classic version that you can get printed. There's also wall charts available. There's a nice version on the internet that allows you to drill down in and see various things. You can see here that this island of stability is where these things are black in color. And if I get too far off on either side, they change. So really, we actually talked about two types of decay in the nucleus. There's really a third major type in which, excuse me, in which the very heavy things will throw off a helium nucleus, an alpha particle by itself. That particle is very well bonded, and it will actually come off as one unit. That only happens in the heavier isotopes. Then there's spontaneous fission and a few other things. Most of the gamma rays that are produced are really produced secondary as transitions of electrons between states. Dr. Imel last time mentioned that all of this radiation, as far as gamma rays go, is nothing more than electromagnetic radiation, the same as the light you see around you, except for at higher energies. Now, there is one significant difference, and one of the reasons that we're a little careful around this high energy radiation is once the radiation gets up to a high enough level, then it has the ability to do what we say is ionizing, meaning that it can come in and it can knock an electron off an atom. And it's the ionization that causes the damage. So what really happens from radiation damage is you're coming in and you're knocking off these electrons, which now leave positive ions, things in a positive state, which causes chemical interactions that wouldn't normally happen to occur. So the damage that occurs is chemical in nature, but is driven by these ionization events. I just pulled up a Google search and did a search for chart of the nuclides. If you do that, you can pull up this picture. Welcome to play with it. Drill down in and look. You can actually, there's a lot of information there. If I start drilling down, at some point I should get text on there telling me what's going on. All right, we see individual elements down here. Lead. See, all of these leads are actually stable. Different numbers of neutrons. If I look over here, that says 82 protons, and down here is the neutron count. And what we usually talk about is the atomic mass of an element. So, lead 207 there, for instance, consists of 82 protons and 125 neutrons to give a total of 207. When you get down there deep enough, there's various information that's you can pull off this chart. You can look at radioactive decays. And really, there's a wealth of information here. I'm not going to go too far into that. I prepared a little PowerPoint presentation. Let's go to that. Let's see, from the beginning. Where does energy come from? What sources of energy do we have at our disposal? We really only have one, and that's the sun. Right? The sun drives all else. The fossil fuels that we use are nothing more than stored solar energy. Well, from the beginning when we were burning wood, basically what's happening is the plants and trees are taking energy from the sun, combining that with CO2 from the atmosphere, and creating this carbonous form of energy wood that we then take down and burn, combine it with oxygen, change it back into CO2, and liberate that energy that was stored. It takes energy to grow that plant, and that energy comes from sunlight, and then we liberate that when we burn it. The fossil fuel we burn in our car is the same thing, except for it's been stored for millennia. That years ago plant material and animals metabolized this CO2, grew, died, that stuff was buried. In the case of coal, lots of plant material was buried, and then that material was crushed and solidified. We pull that material up and burn it. What we're doing is we're releasing CO2 into the environment. You've heard this, everybody talk about the energy crisis and trying to eliminate the CO2. If you take things like wood and you burn them in your wood stove, you're releasing CO2 in the environment, but that CO2 is not primordial, it's modern. That CO2 that's released would happen anyway. When that plant fell down on the ground and decayed, that same CO2 would be released. Where people claim we're causing problems is by burning fossil fuels, that we're liberating CO2 that's been locked up underground for millions of years. And the model is that will return us by increasing the CO2 temperature, or CO2 concentrations, absorbing more sunlight, will increase the heat of the planet and bring us back to those times millions of years ago when things were much warmer and the dinosaurs were around. So that's a little background. I guess you guys can see this presentation in Pocatello. So, how do we really move around or power ourselves today? Our primary source of energy is combustion. That doesn't really matter. It's all hydrocarbon combustion, most of it. And so one is about as good as the next. I picked a real simple example of methane. But if I were to burn the fossil fuels, they just have long carbon chains and there's more molecules there. They're very convenient, high-density energy storage. Very mobile and easy to use. But the amount of energy released per rearranging these carbon bonds is similar in nature. So if we look at this, I just did a simple chemistry equation where I took CH4 and I balanced that with 2 moles of O2. Okay? You see this 3.76 times 2 moles of N2. That's just a shorthand, because for every mole of O2 in the atmosphere, there's 3.76 moles of N2. About 80% nitrogen, 20% oxygen. So ideally, this nitrogen would go along for the ride and not participate in the reaction. But it's there in the air, and we're burning it with air, so let's take it along for the ride. And so that stuff would rearrange, and if combustion ended up completing perfectly, I'd have CO2 and water. Okay? If I got rid of the carbon and burned just hydrogen, I would get rid of the CO2, and I would end up with just water coming out, plus some nitrogen, plus some Q or some energy. Now, things are never perfect. A lot of times the combustion doesn't fully complete, so we end up with partial products of combustion. We end up with CO. We end up with HO, other things that are partially there. The nitrogen ideally would go through this process unburnt or unchanged. However, at higher temperatures, the nitrogen will dissociate from each other. And then that can react with the oxygen, and we get these oxides of nitrogen, the NOx's, which also contribute to greenhouse. One of the advantages of a thing you've heard called, or a fuel cell, is the fuel cell really completes this combustion reaction at low temperatures. And since it's low temperatures, even if there's nitrogen around, the nitrogen won't dissociate, and so it won't participate in the reaction. And we would hopefully get pure CO2 and H2 if we were using a carbon as fuel. The energy that's released for that reaction, that Q, is about 3 or 4 electron volts, somewhere in there, depending on the reaction. And that's a reflection of how much energy it takes to change or rearrange these electrons in the electron cloud. If I were to do this in terms of energy density, in this case it's about 1/4 of an EV per AMU of fuel, atomic mass unit, because we have so many moles of this material participating in, or atoms, which releases about that 3 to 4 EV. Approximately 54 million joules per kilogram. That's the energy that we get from burning methane. Okay? Let's compare that to fission. A fission is a process where we take a heavy element, and there's very few that we'll call fissile. I'll define that in a minute. And we split it apart. And so these elements normally would decay by alpha decay, emitting a alpha particle, and then would go for 3 or 4, now more than that, 7 or 8 decays and end up as lead. But if I tickle it just a little bit, I can get it to undergo this fission process, which means it splits in half. Not quite in half, but it splits into 2 pieces. So I have to have something that I can tickle it with. I have to have something that I can get in there and split it apart. I can't really shoot electrons at it. I can't really shoot protons at it. If I shoot protons at it, the center of that nucleus has a very large positive charge. In the case of uranium, it's 92. And so a proton is just going to veer off. So the neutron is the perfect thing to use to split this atom. Neutrons also have their problems. Because they don't have a charge, I can't really control them. I can't really aim them very well and direct them with magnetic fields. But if I take a neutron and I can introduce it into a bunch of uranium, I can get this reaction to happen and they split. And I end up with 2 pieces, X and Y. They vary a little bit. There's a spread of elements, as I'll show you. Plus about 3 extra neutrons that come off that are loose. Plus some energy. Now the interesting thing here is the energy. Remember, I had 3 or 4 electron volts. In this case, I get 200 million electron volts. Of that, about 168 million are recoverable that show up as kinetic energy of the fission fragments themselves. And I can recover those as heat. 200 million. Compare that to 3 or 4, not 3 or 4 million, 3 or 4 for combustion. In terms of amount of energy per AMU involved, or in this case 235 plus 1, 236, I'm looking at about 850,000 EV. Compare that to 1/4, or about 8.2 times 10 to the 13th. That's a factor of 10 to the 7th difference per kilogram. 10 million times more energy output per kilogram for fission. Can we think, is there anything better than that? Anything more than that? Yeah, there is actually. Fusion. Now I picked one particular reaction of fusion that has very high output, and it's also the most likely we can get to happen. But it entails fusing 2 isotopes of hydrogen. Hydrogen with 1 neutron we call deuterium. There's a lot of deuterium around. There's a small fraction of natural water that contains deuterium. And you can fuse deuterium directly, but it's a little harder to do than this one. We haven't been able to bring this one about in a controlled fashion. One can do a pretty easy calculation with the natural abundance of deuterium and find that in 1 8-ounce glass of water, if you could fuse all the deuterium together, much less the hydrogen, just the deuterium together, the amount of energy contained in every glass of water is about equivalent to 500 gallons of gasoline. Phenomenal. And we have plenty of water if we could get this to happen. In this case, we're combining deuterium with a tritium atom. Tritium is another isotope of hydrogen. It has a very short half-life, so I really have to create it. And it has a proton and 2 neutrons with about a 12.5 to 13-year half-life. If we combine those two together, we produce an alpha particle, which is the helium nucleus, plus an extra neutron, plus some energy. And that energy is 17.6 MeV. You know, I mentioned before, it's more energetic. That's a lot less than 200. But there's a lot less mass involved here, too. So that's 17.6 million electron volts for an investment of 5 AMU. 3.52 MeV per AMU. 3.4 times 10 to the 14th. Another order of magnitude higher. Joules per kilogram. Now there's some problems with this. They're trying to bring this off. Hopefully we'll get to a point where we'll talk about fusion efforts. There's a couple of big efforts going together to try to make this happen right now. There's a big tokamak that's about ready to fire up in the next couple of years where they may be able to reach break even. There's also another effort called inertial confinement, which the idea is to bring this event and make it happen so fast before it has a chance to fly apart. So they have a facility that's huge, producing ultra high intensity lasers, that they're going to all focus these lasers onto a single little blip of this deuterium and tritium and cause it to burn. And as it burns and ablates away the outside, a wave of compression will go down to the center of the pellet and cause it to ignite. So there are people who've been chasing this. We've been chasing it for 50 years. We haven't been able to bring it off in a controlled fashion that we can get energy out of. But boy, the potential is wonderful. The potential is great if we could do that. Hopefully we'll have a chance towards the end to talk about that. Dr. Imo brought up this curve before, this binding energy curve. I wanted to touch on it a little more because it's pretty important. Really, it's kind of gives a lot of insights into the way the entire universe works. What this is, and I've written down below what that curve actually is. Okay? So what I've got down here is n, or the number of neutrons, times the mass of a neutron, plus the number of protons times the mass of a proton. And I'm going to subtract off of that the mass of the atom itself. So we call this a mass defect, meaning that the atoms themselves weigh less than their building blocks. Okay? If I divide that by the total number of nucleons and multiply it by c squared, from Einstein's famous E equals mc squared, to come up with an energy. And then I plot that result, and I get this curve. But what's interesting about this curve is it shows a peak at iron. Okay? What does that mean? That means that the average weight of a nucleon is less in iron than anywhere else. That if I were to take the weight of an iron molecule and divide it by the total number of nucleons, so I get an average per nucleon, it's slightly smaller for iron. If I start getting heavier than iron, then the average weight of a nucleon goes up. If I get less, the average weight of a nucleon goes up. Iron, I get the most particles for the least mass. That makes it more stable. Anything that I do to take elements and move them towards the center produces a lighter average for those nucleons. And that difference in mass shows up as energy. Anything I went the other direction and tried to go from iron either smaller or larger requires me to put in energy to make that happen. And that energy will show up as mass. So I can't get any energy out of iron. It's at its base state. It's at the lowest potential. Everything else is if I can make it go towards iron, I can get energy out. Wow. So, we define two things. On the low side of the curve, we have fusion, where we put things together. That's how we power our world. The sun produces this fusion energy. The fusion energy transmits the radiation to us. And nature's very clever about using that radiation to power ourselves, plants and animals, and our fossil fuel. The sun will continue to fuse elements bigger and bigger and bigger. Well, our sun won't, it's too small. But large suns will continue to fuse these elements until we get to iron. Once we've hit this iron barrier, we're stuck. There's no more energy to be gained. I can't fuse things together and make larger elements. So where did they come from? If the Big Bang event produced nothing but helium and mostly hydrogen, and then suns fuse things up through iron and run out of gas, why is there stuff up there higher? The best model we have is that the energy is required to fuse. Remember, I can fuse two irons together and get something huge. There's just no energy there to be had by doing it. So it takes energy. Well, at the last gasps of a sun, when it's reached the iron barrier, then gravity takes over, the sun collapses in supernovas, and in that event, energies are high enough that we get some of this material created. And so by very virtue of having this material around, means that we're second generation. We're built literally of stardust. We're built of the last generations of stars that then formed into this current solar system and stars. Kind of neat. We are literally made of stardust, or we're literally made of nuclear waste, whichever you care to look at. All right, so quickly, I've got a few minutes. I get on my soapbox and start philosophizing and don't get through what I'm meant to say. So, let's look at how a neutron can interact with a nucleus. Pretty simple. It can either scatter, means it bounces off, or it can absorb. When it is absorbed, that extra neutron sticks in the nucleus and it increases its mass number. Becomes a different isotope. Those isotopes sometimes are unstable. In the case of uranium-235, I slam it with a neutron, it becomes uranium-236. The uranium-236 is very unstable. For all isotopes above mass number 56, there's a threshold energy that can cause fission. For some isotopes that we call fissile, the binding energy absorbing that neutron is enough. We call these things fissile. So, in the case of uranium-235, it absorbs the neutron, it becomes uranium-236. It then starts to wobble and come apart and causes fission. Now, that uranium-230, that neutron doesn't need to have energy in order to make that happen. And in fact, the probability of that interaction occurring goes up drastically as the energy is removed and the neutron's just wandering around in equilibrium. Now, other isotopes can also fission, but it requires energy. Shoot, I can fission lead. I can take lead and fission it and get energy out. Problem is, it's not likely to happen, and I need one heck of an energetic neutron to do it. It takes us to bring a lot of energy in there to fission the lead. Where this, what I really need to do is just bring a neutron around it and remove the energy from that neutron so it spends enough time in the vicinity to interact. And then it gets gobbled up and the fission occurs. There's really three of these elements that are important, we call fissile. Of those, there's only one with a long enough half-life that we still find much abundance on the Earth. So again, this definition of fissile is an element that can undergo fission by absorbing a neutron with zero energy. Fissionable means that the element can fission, but the neutron has to bring energy. So really, we can make the reaction happen with only fissile material. Uranium-235 being the most important. there are still small amounts of uranium-235 around that we can use. If we would have spent another 1,000,000 or 2,000,000 years in the trees, that uranium content would decrease and it'd be harder and harder to bring this about. In the past, the uranium content was higher. The uranium-238 is also radioactive, but with a longer half-life. So, over time, the ratios of 235 to 238 go down. We currently need to increase those, as well, maybe I'll talk about here. There's a couple of others, uranium-233 and plutonium-239, both of which have short enough half-life for tens of thousands of years, but we don't find them in nature anymore. So we kind of have to make them. Okay, fissionable thorium and 238. All right, so neutron hits the 235, becomes 236. It oscillates, it splits off, and gives a couple of extra neutrons. Now, if I can take those neutrons, and those fission fragments are very heavy, lots of the energy contained, and these neutrons, few gammas, 200 MeV. If I can, these fission fragments will interact very rapidly and cause a lot of heat, so I can use that heat as a power source. Here's a plot of the distribution of fission fragments. Note that the element doesn't break in half. It breaks into two sections. One at about 135 mass number and the other one down about 70, something like that. Notice it's a logarithmic curve. So the probability of it breaking right in half there is almost 2 orders of magnitude. Less than 1% break directly in half. Most of them break into two sections that one's larger than the other. Another point here is because of the way this island of stability on the chart of the nuclides is laid out, all of these elements up here tend to be neutron heavy. Because it takes more and more neutrons the heavier I get. So these big elements have lots of neutrons. When I split them in half, both halves have too many neutrons to be stable. So they're going to undergo a series of decays to move them back to stability. And the primary mechanism for these fission fragments is this beta decay. Since there are too many neutrons, a neutron comes apart and they walk towards the island of stability. Hundreds of fission fragments. The idea of a chain reaction. So how to make this reaction self-sustaining? Well, I get these 2 or 3 neutrons that come out. In order to make it self-sustaining, I need to capture one of those neutrons. One of those neutrons needs to turn around, hit another uranium atom, and cause that atom to react. Now, the probability of those reactions occurring goes up drastically as energy drops off. So what I really want to do is take these 2 to 3 neutrons that are born at high energy. You can imagine when this thing comes apart, there's 200 MeV of energy there. These neutrons are flying with on the order of 2 or 3 MeV apiece. Lots of energy goes out to the fission fragments as well. I want to slow these neutrons down so they'll be absorbed. These neutrons fly all over the place. And they don't ionize very well, so really they don't slow down anywhere near as fast as the fission fragments. So what I need to do is bounce these around and make them slow down. Remember, originally I said that an atom can either be scattered or bounce, or it can be absorbed. Well, if I were to take and want to slow these things down, what should I hit them against to slow them down? Let's think about a simple example. If I filled this room with bowling balls and I threw a ping pong ball out there, the ping pong ball would bounce all around and take hundreds of bounces to slow down because it doesn't impart a great deal of its energy to the bowling ball. It would hit that bowling ball and come straight back at me. So it would take a lot of collisions for that puny little light neutron to slow down if it's bouncing around uranium. If I take that same ping pong ball and I throw it out into a bunch of ping pong balls, hits one ping pong ball, that ping pong ball takes off. And you lose on average half the energy. So it takes very few collisions slamming this ping pong ball into other ping pong balls to remove that energy. So I want light material in my reactor that we can slow these neutrons down rapidly and hopefully keep them in there so they can be reabsorbed. Which works out very well because we can surround this with water. Plenty of water. It's an excellent conduction mechanism to get the heat out. We're very familiar from our coal-fired plants of boiling water, creating steam and running turbines. So we use water in these plants to moderate and slow down the neutrons. So we can get another chain reaction. All right, neutrons slowing down. Here I talk faster than my slides, so we can skip through them. Okay, light material, we call this a moderator. Heavy material is a poor moderator. Remember, we have 2 to 3. Well, 2 or 3 of these neutrons, all of them would initiate another reaction. The number of reactions, the energy levels would blossom exponentially. So some may leave, some not all are absorbed, some may leak out of the system. Some may be captured in other materials and not lead to fission. Some may have some other reactions. You've all heard this term criticality. And this is one thing that really kind of gripes me when I listen to the science fiction movies. I always say, oh, the reactor is going to go critical. Well, yes, every reactor has to go critical or it isn't a reactor. Critical simply means that this criticality constant multiplication factor we call K is equal to 1, meaning that there's a constant number of neutrons from one generation to the other. A reactor that doesn't go critical is not much fun. Doesn't do much. Won't sustain a chain reaction. So K is nothing more than this ratio, this multiplication factor. If K is equal to 1, a reactor is critical. If K is less than 1, we call it subcritical, meaning that power levels are dying off. If K is greater than 1, we call it supercritical, and the neutron population is growing. So every reactor also goes supercritical. All that means is it's coming up in power. We couldn't increase the power levels and use it as a power source. We couldn't make it go supercritical. To complete this thought, what they really mean, I don't have time to get into it, is a problem. There's a distinction in how fast it happens. That the time it takes a neutron in uranium to come out from fission, slow down and be absorbed, is about 1/10 of a millisecond, meaning there's 10,000 generations in a second. And so if I went even 1% supercritical, that power level would bloom so fast that I couldn't control it. Luckily for us, not all of these neutrons that we use come out promptly at the fission event. There's a few that come about as decay of some of these fission fragments, and that has a fairly long time associated with it, on the order of seconds. That's what allows us to control this reaction. So what they probably mean to say is not that the reactor is going to go critical, it's the reactor is going to go prompt critical, meaning that it can sustain its reaction on prompt neutrons alone. That's a bad thing. If we stay supercritical between K equals 1 and K equals prompt critical, then we can have a reaction we can control. So all modern reactors are limited, that I cannot induce or introduce enough positive reactivity to make it go prompt critical. Not all of them. Sometimes in the research world, the trigger reactors, for instance, will do this on purpose in pulse. I invite you to go to YouTube and do a search for trigger pulse. There's some interesting videos of that. If you have questions, ask me later. Okay, so a reactor maintains this controlled fission. We control this by putting in something with a very large absorption cross-section and moving it in and out, like a sponge that would soak up these neutrons. So we can control the reaction. Now, a very important thing. You've all heard the term enriched uranium. Iran is trying to enrich uranium. What does this mean? Well, naturally, most of the uranium we have is uranium-238. 0.7% is uranium-235. It's very difficult to enrich this stuff because it behaves the same chemically. Okay? As I alluded to before, in the past, the amount of uranium in the fuel was greater, uranium-235. Currently in our light water reactors, we want to enrich between 3 and 5% uranium-235. If I extrapolate back in time several millions of years, there was a time when natural uranium was 3 or 5%. We actually see evidence of naturally occurring fission reactors in the open that ran for millions of years, where just veins of uranium would be covered with water, spontaneously undergo fission, create fission fragments, produce energy, and dissipate. In our current light water reactors, we want 3 to 5% of this material to be uranium-235. If we wanted to build a bomb, I'd want that amount to be 95% plus. So I'd really have to do a lot of work to get rid of all the 238 and just create 235. The 238 we call depleted uranium. We use it for munitions. So one of the problems here is that we take this fuel and we have 3 to 5% useful material. Now that 3 to 5% useful material we burn up in the reactor and then we get rid of it. Currently, the plans are to store all of that. Used to be we're going to store it in Yucca Mountain. Now that plan has been put on hold, if not killed, so there's nowhere to store it. So currently all this material sits at the reactor sites where it's been burnt. But think about this. Only 3 to 5% of that material is the actual fuel. The rest of the uranium comes through this. So very little of this material gets burnt because this uranium-238 isn't fissile. Okay? But there's something neat that happens in that the uranium-238 can absorb a neutron and become uranium-239. It doesn't fission unless that neutron has a lot of energy. But a small amount of it can be absorbed and become uranium-239. The uranium-239 then has a beta decay to become neptunium. The neptunium then has another beta decay and becomes plutonium-239. So remember, plutonium is another useful fuel. And also, plutonium is different than uranium. It has another couple of electrons, so I can separate it with chemistry. That has a half-life of 24,000 years. So a natural consequence of this reactor, and every light water reactor does it, every reactor with uranium-238 does this, is it converts some of this useless material to plutonium. Now in our light power reactors, that plutonium is burned up as soon as it's made, because it's as fissile as the uranium. In fact, at the end of life, there's about as much uranium as plutonium in the fuel. One of the neat things that can happen, though, if we design the reactor properly, and that was done out here in Idaho. The breeder reactors out here, the first ones to produce power, were doing so in such a way that the conversion ratio was over 1, meaning that they were taking useless uranium-238 and they were converting it into plutonium-239 at a rate faster than they were burning the plutonium to make power. You will never find in engineering anything closer to a free lunch than that. That I'm taking useful material, useless material, converting it to useful fuel and getting energy out at the same time. It's like I could fill my gas tank with water, drive across the country and fill somebody else's vehicle up with the useful fuel I'd produced. Now, it's not like water because there is energy here. Water, there isn't energy if I'm converting it to hydrogen. So, if we were doing this, which a lot of the world is, okay, that would really increase the amount of energy that's there. And more so than that, think about what it does to the nuclear waste problem. By doing this and reprocessing the fuel, we take this massive waste that we have to hold on to and protect, and we drastically reduce it. We can get down easily to 10% of the original mass. And by the way, that 10% of the fission fragments all have shorter half-lives We don't have to store them so long. The problem are these transuranics with billions of year half-lives. But we can take this material and burn it. We don't do it. We could take all the depleted uranium. We could burn that. Now we make it into bullets. And, by the way, we use it for ballast. They take chunks of depleted uranium and they put them in planes and fly them overhead to balance the fuselage. What's more than that, there's a whole other cycle here. Thorium. There's more thorium in the Earth than there is uranium. There's no fissile elements of thorium left. All thorium is thorium-232. Everything else is decayed away. Thorium, again, is radioactive with a very long half-life. But it will undergo a same kind of reaction. Absorb a neutron, become thorium-233. Go through a beta decay to become protactinium-233. Go through another beta decay to become uranium-233 with a 150,000 year half-life. That material is also fissile. That material also can be used as a fuel. And there's something even neater about this compared to the cycle to breed plutonium, is that this material can be bred at thermal energies, meaning it can be bred in a light water reactor, where to actually make effective breeding ratios with a plutonium fuel cycle, you have to breed at higher energies for reasons I don't have time to get into, but you have to moderate with something other than water. In the case out here on the desert, they moderated with sodium. Now, the other people who have talked to me, particularly Lineberry, was not involved in the original EBR-1, but he definitely was involved in the fast reactor days, EBR-2, when they perfected this technology. So we have a wealth of knowledge here in this department. The tools we really need to produce the energy we need were developed here in Idaho. They're now being used through the rest of the world. It's kind of a shame that we don't have the political will to go back to this technology, which really is about the only thing that can scale to save us. Okay. Any questions? I ran out of time. It's what you guys probably feel like. I'm up here like a rabid dog. We're all happy to answer questions. I'll hang around through some of the rest of it. If you don't ask for questions, nobody has them. So I guess that means you were probably completely over your head. It was fast and furious. Sorry.